this is one of the high points of the course in terms of applications. We want to learn how to solve optimization problems. We want to figure out what values are best. And so the point of today's class is to see how to solve these problems. Okay? So how many of you are interested in economics? All right, so in some of your econ classes, you should hopefully see this in the future. So this is going to be an important lecture. How do you find optimization in one dimension? What do you do? So again, whenever we do something in higher dimensions, we always start off with lower dimensions. So review of one dimension. What do we do in one dimension to find maxima and minima? I'm sorry?
Take the derivative and set it equal to 0. Find critical points.
Thank you. I didn't want to run into the door again. So 1, it's critical points. And 2, it's check endpoints. And again, it's very important to remember these only give you candidates for maxima and minima. They don't necessarily give you the points where the maxima and minima are obtained. So for example, the danger is something like this. F of x is x cubed. So this has no max and it has no minimum. No max or min at the critical point x equals 0. And, f prime of x is just 3x squared. So unfortunately, just because you're at a critical point doesn't mean you found a maxima or minima. But what it does mean is you're at a good point to check. And the whole purpose of all this calculus is to winnow down the list of possibilities. So now let's go to several variables. And just like one dimension, we have two situations. We could be at an interior point, or we could be on a boundary point. So maybe this boundary is where g of x is fixed and equal to c, and I want to find the maximum or the minimum values of f. How do I find a maximum or minimum value of f if I'm inside? Where are my candidates? So where are the candidates for the maxima and minima inside? So what's the generalization from one dimension? Yes?
Do you look at the partial derivative?
Good. And so what should the partial derivatives equal?
Oh,
0. So for the interior candidates, we want the gradient of f at x to be 0. There's a nice way we can interpret this now that we've done directional derivatives. The directional derivative of f in the direction of v at x, such lovely notation, is the gradient of f at x dotted with v. Well, if the gradient of f happens to be 0, what's true about all the directional derivatives? So they're all 0. If the gradient of f at x is 0, all directional derivatives are 0. So what that tells you is I'm at some point, bless you, and no matter which direction I move in the interior, all my directional derivatives are 0. That's a really nice analog of what was going on from Calc 1. And so this is a nice consequence of the gradient of f has to be 0. Now is the difficult part, is how do we handle the situation of being on the boundary? So if we're on the boundary, we have this constraint. It's not just enough to find where f is largest. We want to find the maximum. We want to find where f is largest subject to being on some constraint. So here's the setup. We have a function f to maximize or minimize. And we have a constraint g, i.e. g of x is equal to c. So if you want, imagine that now we're on the surface of the sphere. And we have to stay on the surface of the sphere, and we want to know, of all points on the surface of the sphere, where is my function f largest? So before, when we were in the interior, life was very nice. I could move in any direction I want. I'm in the interior. On the boundary, however, if I move in a certain direction, I'm not going to stay on the boundary. I'm going to move off my constraint. Okay? So that's what makes it so difficult, is we have to not just find where f is largest and smallest, but it has to be at the same time satisfying this constraint g of x equals c. All right. So one of the nice things about teaching in class twice is you can mix things up a little bit. I'm going to do things in a slightly different order than I did at 10 o'clock, and just to see how this helps. So here is some curve. So think of this is my curve, g of x equals c. Okay? At every point, I can draw the normal direction. Okay? So really, I should be drawing a two-dimensional curve, two-dimensional surface, or maybe a five-dimensional surface. My artwork just is not that good. I'm going to just draw a straight line or a curvy line and just imagine that there's other directions as well. Okay? So this is my surface, my gradient of g that points in the direction of the normal. If I want to stay in the surface, I can't move normal to the surface. I have to move tangent to the surface. So at every moment in time, I can draw my tangent vector as to which direction I'm going. Okay? Now, I know how I have to move to stay on my curve. Imagine I'm at this point, and let's calculate the gradient of f. And imagine the gradient of f is pointing in this direction. Well, if the gradient of f is pointing in this direction, I can write it as something in the direction of gradient of g plus something in the direction of the tangent. The normal is perpendicular to the tangent. Think of this as we were in Manhattan. We have our north-south and we have our east-west. And so I can write my gradient as something north-south, something east-west. If you look at this, the gradient of f has a component in the direction of the tangent. Let's think what would happen. If my directional derivative is positive, can I be at a maximum? So say my directional derivative is 5. Why can't I be at a maximum?
If you move more, you'll have a higher number.
Okay, so if I move in that direction, I'll go up. And if I move backwards, what will happen? I'll go down, so I can't be at a minimum. So over here, because my gradient has something in the direction of the tangent, my directional derivative is not 0. The dot product is not going to be 0. Oh, if the dot product is not 0, this can't be a maximum. This can't be a minimum. Let's keep moving. Over here, let's say my gradient of f is like this. Could I be at a maximum? No. I have something in the direction of the tangent vector. Keep moving. Now I come over here, and imagine my gradient of f. It's enormous. It's huge. It's wonderfully large. But it's in the same direction as the gradient of g. Is there any component in the tangent direction? No. What's the directional derivative going to be? 0. We found a candidate. Okay? So if the directional derivative is non-zero, it can't be a maximum or minimum. If the directional derivative is 0, we have a candidate. So candidates are where the gradient of f is parallel to the gradient of g. Okay? This is basically this is Lagrange multipliers. Right? We're going to do it more formally now, but this is the intuition behind why Lagrange multipliers work. If I'm moving along and my directional derivative is not 0, I can't be at a maximum or minimum. So I keep moving until I reach a place where my directional derivatives are 0. So now let's do it more formally. So the method of Lagrange multipliers. probably the most important part of the method of Lagrange multipliers is pronouncing Lagrange's name correctly. It is not Lagrange. Okay? When you are a mathematician of this stature of Lagrange, you have to learn how to pronounce the person's name correctly. Okay? So if you really want to get me upset, call him Lagrange. Right? Now, if you want to take certain people who write postmodern stuff, by all means, butcher their names. But Lagrange is in a separate category. Right? So here's the framework. So before we do any theorems, you always clearly state the conditions. So here, f and g will be functions from Rn to R. They'll be differentiable. And we require g of x to equal c. So we've seen a phrase to describe the set of points such that g of x equals c. What phrase is that? So the phrase g of x equals c. The level set. All right, we're going to get dividends again from all that stuff we've done earlier. We're looking at a level set. The level set might be a sphere, it might be an ellipse, it might be a hyperboloid. We require g of x equals c. Then candidates for max min are x naught such that the following two conditions hold. And again, actually, let me do this more clear. Candidates for maximum minimum of f of x subject to g of x equals c are x naught such that, okay. So again, I'm searching for maximum and minimum of f subject to g of x equals c. And so there are two things that must be true. One of them is almost a no-brainer. It's staring at us right now. We're trying to maximize f subject to g of x equals c. So if x naught is a candidate, you know something about x naught. What's the thing you know must be true? So we're trying to maximize f subject to our point must satisfy g of x equals c. So what do you know about x naught? So what's its relation with g? What must be true about g of x naught? What must that equal? It must equal c, right? This is the method of Lagrange multipliers. We're trying to maximize our function f subject to g of x equals c. So if x naught is one of our candidates, it has to satisfy g of x naught equals c. This is often forgotten by people when they go through the calculations, and it's disastrous to forget this. And we'll see why in a moment. The second one is there is a lambda such that the gradient of f at x naught is lambda gradient of g at x naught. So that's the more interesting condition, that if you at a candidate, the gradient of f and the gradient of g are parallel. What does it mean for two vectors to be parallel? They point in the same direction, but they can have different lengths. How do you rescale the length of a vector? You multiply it by a number. If I want it to be 5 times larger, I multiply by 5. If I want it to be 6 times larger, I multiply by 6. So if grad f and grad g are supposed to have the same length, then the way to do this is to say, to have the same direction, to say, well, look, they've got to be parallel. So that means if I rescale the length of the grad g by something, then that's going to be the same as my vector grad f. That's what it means for two vectors to be parallel. Their lengths just differ by a multiple. Okay, so this is Lagrange multipliers. Let's see if it's reasonable. Can we expect this to work? So the question is, how many variables, how many equations? So my point x naught is some n tuple of numbers, x1 through xn. Okay, I have some n tuple of numbers. Do we have any other variables? Is there any other unknowns that we have? And we're trying to find this point x naught. It's got coordinates x1 through xn. Is there any other unknown? Yes? Nope. Because I'm telling you, you have to be on the surface g of x equals c. So I have to tell you what the value of c is. So c is a given.
The lambda?
The lambda. Lambda is also unknown. I am violating something I try not to do. I am discriminating. But I'm discriminating in a way which is acceptable. Okay? Lambda to me is not as good as the variables x0 through xn. I mean x1, x2, x3, xn. So you ask me which of my kids do I love the most, I will not answer a question like that, typically. This, however, I will answer. I love x1 through xn much more than I love lambda. Why? Why doesn't lambda get the same amount of love as x1 through xn? So you should always know what your purpose is. What is your goal? What are you trying to do? What's our goal? What are we trying to find? The maximum of what? Of f. So we're trying to find the point x1 through xn, right? This is why I don't love lambda as much as I love x1 through xn. My goal is to find x1 through xn. My goal is not to find lambda. I'm happy to find lambda if finding lambda helps me find x1 through xn. Sure. But my goal is not to find lambda. All right? So these are my n plus 1 equations. I'm sorry, n plus 1 variables. N plus 1 variables. Now let's count equations. So one equation is obvious. I have g of x naught equals c. So that's my first equation. And this is where I now have to use the fact that c is given. I know this equation. So I have g of x naught equals c. And now I'm going to unwind this grad f is a multiple of grad g. I get df dx1 at x naught equals lambda dg dx1 at x naught, dot, 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 df dxn at x naught is lambda dg dxn at x naught. This is unwinding the grad f equals lambda grad g. Grad f and grad g have n components. I get n equations. So how many equations do I have overall? N plus 1 equations. Hey, this is pretty good. I have n plus 1 variables. I have n plus 1 equations. There's hope. Okay? Imagine I had one variable and two equations. Do you expect to be able to solve for one variable with two equations? So I give you maybe 3x equals 1, 2x equals 221. Do I expect to be able to solve this and find a value for x? No, right? I have two equations but only one unknown. The system is overdetermined. So if more equations than unknowns, typically overdetermined, so expect 0 solutions. So if we have more equations than unknowns, we don't expect things to work out. What if we have more variables than equations? So more variables than equations, what if I gave you 2x plus y equals 1? Do you expect to be able to solve that? Do you expect there to be solutions to 2x plus y equals 1? Can somebody give me a solution to 2x plus y equals 1?
So you can write y and x in terms of each other, but you can't find a numerical value for it.
Can you give me a choice of x and y that solves 2x plus y equals 1? Yeah, I can take x equals 0, y equals 1. I can take x equals 1, y equals negative 1. I can take x equals 2, y equals negative 3. I can find x and y. I can solve this equation. I can't solve it uniquely, but I can solve it. This is an underdetermined system. We have more variables than equations. We expect infinitely many solutions. So this was 1. So if more variables than equations, we have a underdetermined system. So expect infinitely many solutions. Okay? So if we have too many equations, it's not good. If we have too few equations, it's also not good. The whole point of all of this was we don't want to check infinitely many points. We start off with infinitely many points on the boundary to check. I don't want to end the day with infinitely many points on the boundary to check. I want to winnow down to just a finite number of points to check. And so if we have more variables than equations, it's bad. So what's the one situation that's left? What haven't we covered? The same number. And so if same number of equations and unknowns, and variables, expect finitely many solutions. And that's fortunately the situation of Lagrange multipliers. We have n plus 1 variables, we have n plus 1 equations. Everything is perfectly balanced. What will happen is we will do very little calculus. The amount of calculus in Lagrange multipliers is minimal. What are we going to mostly be doing? Algebra. Right? Most of the problems is trying to find a clever way to deal with the algebra. But there is hope that this is going to work. Okay? So this is the statement of the method of Lagrange multipliers. This is why it's good that we ended up being balanced with the number of variables and the number of equations. We gave a sketch of a proof over here as to why this condition should work. Is looking at going on some set g of x equals c. We looked at the normal, we looked at the tangents, and we saw that if the gradient of f had something in the direction of the tangent, then we could just flow a little bit further and we're not at a maximum or a minimum. So what I want to do now is I want to do a little bit more formal proof of what we were doing, but it's essentially that argument there. And so it's going to be a nice way to review some of the stuff we've done with chain rule and paths and everything. So proof of Lagrange. We'll call them multipliers. So let S be the level set g of x equals c. Let P of t be any path in S. So if you want, if here's my sphere, here's some path that stays on the surface of the sphere. What can you tell me about this function? What is true about g of P of t? What does that equal? Yes. It equals c. Why? So quantify in a little bit more detail as to why it has to. I agree it has to. Why does it have to? Because it's on the surface. S is all points that evaluate to c under G. P of t stays in S. And so since everything in S evaluates to c, then this has to evaluate to c. So there are two ways to take the derivative of this. This is the Calc 3 side using the chain rule. This is the Calc 1 side where I ask you what's the derivative of a constant. So what's the derivative of a constant? 0. So we get the gradient of g at my point P of t dotted with P prime of t is 0. And the way you should interpret this is if I start off at some point, P prime of t is going to be a tangent to S at that instant. Gradient of g is going to be the normal. The normal is perpendicular to the tangent. And no matter what direction I go, as long as I stay in S, I'm always going to have 0. So the gradient of g is always perpendicular to every tangent direction. So grad g is perpendicular. Well, we'll do it at x. To all tangents to s at x. Okay, what function have we not talked about yet? F of x. We're trying to find the maximum or minimum of f. Probably f should surface somewhere in the proof, right? So now let's consider f of x. And we want to try to find candidates for where f of x has a maximum or minimum. But we can't move in an arbitrary direction. We can only move in directions that keep us in S. If we're at a maximum or minimum, what must be true about all of these directional derivatives so long as we stay in S? So what must be true about the directional derivatives so long as we stay in S? Want to try it? What must be true? Could the directional derivative be positive? So what would happen if the directional derivative were positive? Could that be a maximum? No. We would just move in that direction and we'd get larger. Can the directional derivative be negative? No. We would just go, if the directional derivative is negative, we go in that direction, we get smaller, we go backwards, we get larger. So at a max or min, all directional derivatives vanish if okay, this is the important part. We move in a direction in S. Right? This is the key thing. Imagine the floor is my constraint g of x equals 0. Am I moving in directions that are allowed? What about now? No. Oh, I heard a phone. Okay, so if you need help getting munchkins for next time, let me know. Okay? You're not responsible for, are you normally in the 11 o'clock? Okay, so you're not responsible for munchkins for the 10 o'clock. Okay, so if we move straight up, am I allowed to do that? No. I only know my directional derivative is 0 so long as I stay in the surface S. So we get dv of f at x equals 0 if v is tangent to s at x, i.e. the gradient of f at x dotted with v is 0. Well, look at what's going on here. We have the gradient of g is perpendicular to every tangent direction. We have the gradient of f is perpendicular to every tangent direction. So imagine we live in three-dimensional space. I have a two-dimensional surface. I have my normal, and I have a two-dimensional tangent plane. As long as I stay in the tangent plane, I'm perpendicular to the normal, and this is 0. Over here, if I go in the tangent plane, I'm perpendicular to the gradient of f. So the gradient of f can have no component in the tangent plane. What's the only direction left for the gradient of f to point? It can't have anything in the direction of the tangent plane. Where does it have to point? In the same direction as the normal. It has to point up. So because we have n directions, in n minus 1 different directions, think Manhattan. I hate it, but a nice grid system. In the north-south direction, it's 0. In the east-west direction, it's 0. The only thing left is the up-down. This has to be entirely in the up-down direction. Similarly, we get this has to be entirely in the up-down direction. It's this argument we made over here. If the gradient of f had anything in the direction of the tangent, we wouldn't be at a maximum or minimum. We'd keep flowing. The gradient of f has to align with gradient of g. Therefore, grad f at x naught is parallel to grad g at x naught if have a max min of f at x naught subject to g of x naught is c. Therefore, there's a lambda such that the gradient of f at x naught is just lambda gradient of g at x naught. And that's the proof. Okay, so this is the more formal proof using the chain rule, considering a path on the level set. This is the more informal proof by just saying, well, look, if I have something in the tangent, keep flowing in that direction. Okay, so the whole point is for applications now, all we have to remember is here are my n plus 1 equations, and I have my n plus 1 variables, and now let's just try to solve. Okay, so before we do an example, any questions on the proof? Everybody as happy as they're going to be about the proof? Okay. So the first example is the Farmer-Brown problem. So Farmer-Brown, again, he loves rectangles. He will not consider any pens that are not rectangular. He has 40 meters of fence, and he wants to maximize his area. Later we will meet Farmer Brown's brother, Farmer Bob, who has a slightly different issue. So here's the example. So we have 40 meters of fence, maximize rectangular area. So step one in these problems is draw a picture. Doesn't have to be a great one. Here's x, here's y. What's my constraint? So what would be my constraint for this problem? 2x plus 2y is 40. So I'll write this as g of xy is 2x plus 2y is 40. All right? What else do I need for this problem? I need a function to maximize or minimize. So what should my function f of xy be? X times y. So we are going to do the problem the way it was intended, as a multivariable calculus problem, not as a backdoor trick into one-dimensional calculus. All right? So we have to calculate grad f, grad g. So the gradient of f at the point xy is just yx. The gradient of g at the point xy is just 2, 2. We are now done with calculus. Okay? Wasn't that long. Now it's time for the algebra. So we now write down very carefully our 3 equations and our 3 unknowns. So we have 2x plus 2y equals 40. Now we have the first component has to be lambda times the first component here. So we get y equals lambda times 2. And the second one is x is lambda times 2. So these are our 3 equations and 3 unknowns. When you do these problems long enough, you start to hear voices in your head as to how to do the algebra. Okay? There is something that's very clear for me. I hear something very clearly right now. What's a good thing to note? Okay, why? Yeah, y equals 2 lambda, x equals 2 lambda. So these two combine, and they give us that x equals y. Oh no, we lost lambda. Is that bad? No, we don't care about lambda. Lambda, we don't. Okay? Unless we absolutely need lambda to help. So lambda is helping us, but we don't care that we're losing lambda. We could always find lambda at the end of the day if we cared, but we don't. The goal is to find x and y. Doing something like this is good because it's getting rid of lambda, and it's giving us a relationship between x and y, and that's what we care about. Now we substitute this into 2x plus 2y equals 40. So now we substitute, and what do we get? We get 2x plus 2x equals 40. Therefore, 4x equals 40. Therefore, x equals 10 meters. Therefore, y equals 10 meters. Therefore, the area is 100 meters squared. Okay? And so that's the problem. So this one, the algebra is not that bad. Okay? Any questions on this problem? Okay. What I want to do now is I want to consider the Farmer Bob problem. Have we talked about Aquaman yet? How many of you remember the superhero Aquaman? What are his special powers? He talks to fish, yes. When I was growing up, he had another power. He could actually collect water underneath the water and convert the water into like a ball of water, which he could then throw at bad guys. So when I was young, he at least had a secondary power. It turns out, and you have to read the comic books carefully, Aquaman also loves rectangles. They really don't emphasize this enough, but he really does. So Farmer Bob and Aquaman also love rectangles. Farmer Bob is making a pen for his cows, okay? And he will only consider rectangles. And Farmer Bob's land actually runs right next to a very straight river. So here is the river. Okay? So, right? So this is what Farmer Bob is going to do. Okay? And we will give Bob 20 meters of fence. Bob is the younger brother. He clearly does not deserve as much as his older brother, Brown. Can somebody give me the equations for the Farmer Bob problem? So you're going to have to tell me what the variables are.
2x plus y equals 1.
Okay, so g of xy will be 2x, I'm sorry, what is it? X plus 2y or 2x plus y?
2x plus y.
Oh. I think we should probably do it this way. We'll do it as x plus 2y, good. So you said it should be x plus 2y equals 20 because he has 20 meters of fence. And what function are we maximizing? Okay. So now we go through and we solve this exactly as we did the Farmer Brown problem. It's the same type of algebra. Okay? I claim, however, that you can just look at this and see the answer. Okay? And the answer comes from Aquaman. Okay? At the same time as Farmer Bob is doing this, amazingly, Aquaman is underneath making a pen for his fish at the same time and placing it at the same place. So the whole point of this is to understand this notion of symmetry. This is a very hard concept to grasp. The more times you see it, the better. And Aquaman also has 20 meters of fence. How much fence do Aquaman and Farmer Bob have together? 40 meters. Interestingly, the same amount of fence as Farmer Brown. What kind of shape is Farmer Bob's fence plus Aquaman's fence? Well, it's square if it's optimal. It's square if it's optimal. Aquaman is not the greatest of superheroes, so he may not do optimal. If it was, Batman with his intelligence or Superman, yes, but all we know right now is that it's what? It's a rectangle. So now we have two different optimization problems. He finds the best he can up here. He finds the best he can down here. But if we put it together, they've attacked the original problem. If they don't have it such that this is 5 and this is 10, then the total area is not optimal. And they could do better. So I'm going to leave it to you to try to go through the details and make this argument vigorous. But you will find that x has to be 10 and y has to be 5. So it takes a while to do this rigorously. But it's a really good thing to try to do, to see this beautiful symmetry. Okay. So now it's time for a more interesting example of Lagrange multipliers. And so what I'm going to do now is we're going to have the function f of xy is going to be 3x plus 2y, and g of xy is going to be 4x squared plus 9y squared. So I need to give you a little bit more information. What information do I have to give you? I have to tell you C. I have to tell you what 4x squared plus 9y squared equals. There are infinitely many values for C that I will not accept, as they are not interesting and not worthy of being considered for this class. Somebody give me a bad value for 4x squared plus 9y squared. Yeah, negative number. you give me negative 5. I want to optimize my function f subject to 4x squared plus 9y squared is negative 5. There are no values of x and y such that 4x squared plus 9y squared is negative 5. Right? This is not worthy of our time. What's the first value of c that might be worthy of our time? It turns out it's not, but what's the first value that could conceivably be worthy? 0. So if I take 0, I at least have a point in my level set. My level set is not empty. My level set is also just one point. So given that you are at the point 0, 0, find the point where your function f is largest. This is also not worthy of our time. So somebody give me a value that is worthy. 1. Out of curiosity, how many people have seen Wayne's World? Okay. A little bit more than I thought. Okay, so we now have our value of c. We have our functions f and g. What do we compute? What do we compute? The gradients. So the gradient of f at a point x, y is going to be 3, 2. The gradient of g at the point x, y is going to be, did I change the function from before? I changed the function from before. It doesn't matter. It's going to be 8x and then 18y. All right? So now I have to write down my 3 equations and 3 unknowns. So I have 4x squared plus 9y squared equals 1. 3 has to equal lambda times 8x. And then 2 has to be lambda times 18y. Please don't forget to write the 4x squared plus 9y squared equals 1. This is one of the most common mistakes people make in Lagrange multipliers, and then they get stuck because they don't have enough equations. Okay? It's constrained optimization. You have to remember the constraint. That's one of the things. So again, now you have to find the best path to do the algebra. I'd say there's 2 natural things to try here. Any thoughts? How can I try to solve this? What should I do?
Divide 8x lambda by 18y lambda.
Yeah, so I would take ratios. The other thing you could do is you could multiply this by 2 and this by 3. But rather than doing that, I would rather just take ratios. Now, what do you have to be careful about whenever you do ratios or a division? I'm sorry?
Don't divide by
Yes, we're not in the physics department. We do not divide by 0 here, at least not in public. Could we possibly be dividing by 0? No. I'm sorry? Welcome to priming. Could we possibly be dividing by 0? I guess possibly we could. But if I tell you this equals 2, is there any way lambda could be 0? No. Could y be 0? No. So no danger of division by 0 as lambda, x, and y do not equal 0. So if we take ratios, we get 3 over 2 is lambda 8x over lambda 18y. So 54y is 16x. And so I can divide, you get 27y is 8x. So there's lots of different ways I can do it now. One thing I could do is I could then say, all right, x is equal to 27 over 8 times y. Right? And now that I have that, I can substitute in. So now we substitute. Right? And what will we get? We get 4 times 27 over 8 squared times y squared plus 9y squared equals 1. Okay? At this point, I'm bored. Right? The calculus is long gone, and even the interesting parts of the algebra are gone. at this point I'm going to just have some multiple of y squared equals 1. So how many choices will we have for y squared? For y squared? 1. Y squared is forced upon us. How many choices of y will we get from that choice of y squared? 2. We'll get plus and minus, and then we'll just, once we have the 2 choices for y squared, for y, we then, each choice gives me a choice for x. I plug that in, and then I just have to figure out, do I have a maximum or minimum? So at this point now, it's just some algebra. All right? So I'm going to get 27 squared. Now I'm going to have 8 times 8 is 64, but I get to divide by a 4, so I think that's a 16. Did I do this right? Yes. Plus 9y squared is 1. So I get 27 squared plus 9 times 16 over 16 y squared equals 1. Yes, did I make an algebra mistake? Oh, I did, yes. Thank you. All right, so now we get y is plus or minus the square root of 16 over 27 squared plus 9 times 16. Can we simplify the denominator? Can we pull things out of the square roots? Yes, I don't care. This is what the number is, okay? So now we get 2 candidates. So the first candidate is when we have the plus sign. And we know x is 27/8 of y, so the first candidate is 27/8 times 1 to great 16 over 27 squared plus 9 times 16, and then square root of 16 over 27 squared plus 9 times 16. The second candidate is with the minus sign, minus 27/8 square root of 16 over 27 squared plus 9 times 16, square root of 16 over 27 squared plus 9 times 16. How do I figure out which of these is the max and which of these is the min? Plug it into what? The outlet? What do I plug it into? Always use descriptive words. Plug it into what? What function? Into f, perfect. Plug into f of xy. I claim, however, that if we just look at f of xy, there's no need to substitute in. I can tell which one is going to be max and which is going to be min. Which will be max? So if you, the positive one, our function is 3x plus 2y. So if we take the positive one, everything reinforces. It's a huge positive number. If we take the negative, everything reinforces, and it's a huge negative number. So this will be the max. This will be the min. And you could just plug these into the value if you actually cared about what was the value of the function. Okay? So this is how you do these problems. You write down the equations. You figure out, I have 3 equations, 3 unknowns. You figure out a good way to go through the algebra. And then you just keep hacking away at the algebra until you reach the end. Okay, any questions about this problem? All right, so I want to end the day with just another application of Lagrange multipliers. The details of this problem I'll post online. Imagine you are the supreme commander of the US military forces, and you can deploy the US forces anywhere in the world that you want. What's your goal? So you're on the right track. I want something more specific than global domination. So imagine there's a couple of trouble spots on the world. Maybe you want to minimize your response time to troubles. So we have Amherst here, we have Harvard here, and a couple of other places. We will make the unreasonable assumption that you may deploy your forces anywhere in the world you want. China and a few other countries may have issues with that, but we'll assume for now we can put our forces wherever we want. This is a constrained optimization problem. What's our constraint? Yes? Yeah, we have to be on the surface of the sphere. Now, the Earth is not exactly a sphere, but close enough. How do you measure the distance from one of these points to the troublesome? Do we use our distance formula and look at the sum of the squares of the difference of the coordinates? Why not? You can't go through the Earth. So this becomes a very hard problem if you use the correct distance metric. And this is similar to what we saw when we were doing the method of least squares. Depending on how you measure your error, you can get different answers. If you allow your forces to travel through the Earth's surface, you can get different answers as to the optimal ways to place your fleet. Okay, so we will have the start of integration on Monday. I'll send you what you should be reading. I will reserve some time before the exam on Wednesday to just go over questions on material. So if you do have questions in addition to seeing me, the TAs, the Math Science Resource Center, I will leave time on Wednesday.